Good morning. My name's Don. I'm a senior engineer at SOCIOMANTIC Labs and long-term contributor to the deprogramming language. And I'm going to be talking this morning about metaprogramming in the real world. At the first D conference in 2007, I gave a talk which, like this one, included the word metaprogramming in the title. Metaprogramming is a great word to use if you want to impress people. It makes you sound sophisticated. Now, what is it? Metaprogramming is about programming at compile time, moving as much work as possible from runtime to compile time. Normally, the goal of this is to make our programs run faster. But metaprogramming is also used to make our code more correct by catching logical inconsistencies. So, code that's faster and contains fewer bugs. Very, very cool. We all want this. But what's the catch? The catch is, of course, that traditionally it's difficult to write that kind of code. It's hard to write, hard to debug, and hard to maintain. It's great if you're in a university context where you're surrounded by experts in symbolic logic, but it's not something you'd realistically do much of in production code. Well, back in my 2007 talk, I showed that D's new features had given the language so much power at compile time that it was possible for a library to generate optimal code. And I used mathematical vector operations as an example. But back then, the language was barely explored. In that period, very many features had just been added to the language, and it was easy to find a combination of language features which had never been used before together. My emphasis at that time was on innovation. I think that was true of almost everyone in the D community. We were completely in research mode. But today, in 2013, I come with a very different theme. I'm not going to talk about metaprogramming techniques. Instead, I'll be focusing more on the real world part of my title, the transition from research to production. Now, back in 2007, I was in the solar photovoltaic field. Solar has a lot of interesting things in common with D. Both were always regarded as having a lot of potential and being theoretically attractive. Both were under development for a really long time. And there was always lots of people who wanted each technology to succeed. But in both cases, for very many years, hardly anybody was seriously using it. So I started in solar in 1994. At the time, a few companies were making expensive solar cells to be used on satellites, but outside of space, solar was a cottage industry. A big part of the market was selling solar panels to hippies. 5 years later, we rejoiced when one solar cell manufacturer announced that they'd actually operated profitably over an entire 3-month period. Incredible! Although we believed in the technology and expected that it would eventually become profitable, we didn't know when it would happen, and we sort of didn't believe it. But 5 years after that, the industry boomed. A former colleague put his solar company on the New York Stock Exchange and raised $1 billion. Now, the solar industry was hit very hard by the global financial crisis with some spectacular failures, but even despite it successfully left the labs, and you can see solar modules all around the world. Now, I think that anyone who's been personally involved with the rise of a new technology could tell a similar story. when a technology takes off, it can make the transition from fringe to mainstream more quickly than you believed possible. And many things catch you by surprise. Now, it's my belief that D is currently undergoing this transition from research mode to commercial relevancy. When you're in research mode and trying to make the technology successful, you have to make guesses about what will be important. And you focus most of your attention on those. But inevitably, many of your guesses are wrong. Often, some things you thought were trivial or straightforward turn out to be the difference between success and failure. And the mundane stuff can also take far more effort than you had anticipated. So by far the best way of seeing which of your guesses are wrong is by learning from the experience of the early adopters. And this is what I want to share with you today. For the last year and a half, I've had the privilege of working for one of the early adopters, arguably the big early adopter of D, SOCIOMANTIC Labs. The chance to see how my favourite language performs in the real world was interesting in itself. But I joined the company because I was impressed by the team and the success that they were already having. So before I tell you about which of my guesses were wrong, let me introduce you to SOCIOMANTIC Labs. SOCIOMANTIC Labs was founded in Berlin on April 1st, 2009. No, that's not a joke. We're in the online advertising business, specifically real-time bidding. I'll explain what that is on the next slide. Now, there are three things about SOCIOMANTIC that I think make us an ideal showcase for D. Firstly, although we're in advertising, we are not an advertising company. We're a tech company. That's important. SOCIOMANTIC is not an advertising company who has realised it needs to learn about technology. Rather, the company began with the technology developed during the founders' PhD programs. The founders realised that the tech they developed was a perfect match for the brand new real-time bidding industry. And the technology is based on D. Our back-end technology is 100% D. Secondly, SOCIOMANTIC is global. We are everywhere. We're now serving over 50 markets on all the non-frozen continents. We now have offices in 9 countries. In 4 years, we've grown from the original 3 founders to a staff of about 100. And in our Berlin office, we've got 20-something nationalities. It's a slice of the globe in one room. So, like D, we're global. And thirdly, SOCIOMANTIC is profitable. Anybody can grow at an incredible rate if you throw hundreds of millions of dollars at them. But SOCIOMANTIC has not had that. We've had no investors at all. No debt, no equity, not a cent. This growth has been entirely based on cash flow. And after my experience with the solar industry, I find that incredible. So here we have a company, I'll just let you think about that for a moment. Here we have a company that's entirely based on D, nothing else, and has never had any investment and has expanded over the globe. I mentioned that at SOCIOMANTIC we do real-time bidding. It's an industry that's only been around for a couple of years and was invented as a way to improve the quality of online advertising. Now, as you probably know, most websites are funded through advertising. And, as you also know, traditional online display ads are not very effective, and many of them are absurdly irrelevant. Whenever you've seen an annoying online ad for false teeth, or a combine harvester, or something else you had no interest in, it was from our competitors. But if the ad was for something you actually wanted to buy, it was one of ours, probably. Now, actually, I'm not kidding. We've been very successful because we are very good at predicting what people are actually going to buy. So here's how real-time bidding works. You visit a web page. On the page, there's a blank space for an ad. While the page is loading, an auction is held. The auctioneers are typically Google Ads, Facebook Ad Exchange, or various other ad exchanges. And they ask, who wants this ad space? So based on what we know about that user, we calculate how likely they are to want to buy any of the products that our advertisers are selling. And based on that, we submit a bid. Our competitors make bids as well, and the highest bidder gets to show their ad. When we win, we show an individually customised ad for each user. So no two of the ads that we display are the same. Every single one is different. So, choosing how much to bid is an interesting statistical problem. But there's a challenge. You don't have much time. This auction is happening while the page is still loading. In most of these auctions, you're only allowed 50 milliseconds to place your bid. And that 50 milliseconds includes the time for the auctioneer to transmit the notification across the world and the time for your bid to get back to them. And there's no mercy. If you exceed 50 milliseconds, you are out. And somebody else will get that ad space for a very low price. And this operates on a huge scale. There are billions of auctions per day, and that number is increasing rapidly as more and more of the web changes over to real-time bidding. So to be in this business, you need a big data solution. So the challenge that we have is we need to make a good prediction of how likely this user is to respond to an ad. Our clients include some of the world's largest websites, so there's potentially hundreds and hundreds of millions of different, constantly changing products which we could advertise to them. Which of these products are they most likely to buy? And with what we know about this user's activity and the behaviour of similar users, what's the probability that they'll respond? The more data you have, the better a bid you can make. And with the billions of auctions that we participate in, the total number of data we want to be processing is terabytes per day. So this is what they call, technically, big data. A situation where you've got more data than you can reasonably process in the amount of time you have available. Big data is not as impressive a term as metaprogramming, but it's a buzzword that'll get you a lot more money. Now, it's difficult to get this kind of performance from a classic relational database. Something like MySQL is probably not fast enough and can't easily handle this quantity of data. So all the other serious players in this industry are using an off-the-shelf NoSQL product. Products like HBase, Cassandra, Mongo, Redis, Google's Bigtable. Then they put their effort into working around the performance bottlenecks which they inevitably encounter. We do something a bit different. SOCIOMANTIC created an intrinsically fast solution using D. Our infrastructure was designed to have minimal overheads. We sacrificed generality for raw speed. How well do we do? Remember that you only have 50 milliseconds plus internet latency, or minus internet latency, to place a bid. For comparison, a typical hard disk seek time is 9 milliseconds. But for most bids, we achieve 2 milliseconds or less. Guess how many hard disk seeks we do? Well done. Give that man a beer. So here's our technology stack. We use the D1 Tango runtime plus our own base libraries. We are ruthless in avoiding unnecessary heap activity. After a warm-up period, our programs run with almost no memory allocations. This does not mean that we use manual memory management. We use a concurrent garbage collector developed by Luca, which you heard about on Wednesday. But we give it very little work to do. All of our apps are event-driven and based on fibers. It's actually very similar to what Vladimir talked about in his vibe.d talk. We don't use threads. Most of our activities are I/O bound, and we need to be able to do task switching extremely quickly. And we were able to avoid threads in most cases. In most cases, our infrastructure is embarrassingly parallel. Our big data solution is called Swarm. It keeps all data in memory. And the data is distributed across many servers. So this is a giant in-memory database. One of the compromises that we've made for the sake of speed is to neglect multi-language support. Swarm stores everything in D format. We dump objects into it and we get them out. And if your language can't read D, it can't use our database. And finally, all our processes are stream-based and completely scalable. When our load gets too much, we just add more servers. But our overheads are very low, so our servers run very efficiently. We require far fewer of them than you might expect. And all this infrastructure is written in D. But why? Why is SOCIOMANTIC using D? From SOCIOMANTIC's perspective, D has 3 killer features. First, direct binding to C libraries. It's usually more pleasant to use a C library from D than from C because D is just a nicer language. But it's never worse to use D. You never lose. It's always better or equal. So with this frictionless interface to C, we're never tempted to reinvent the wheel when a perfectly good C library exists. Of course, D is not unique in this regard. Several other languages offer direct binding to C, but not in combination with the next 2 features. The second and the biggest killer feature of D is array slices. We do all our memory management by reusing buffers stored in array slices. If the existing buffer is big enough, we use the same memory we used last time. In the rare cases where we need more memory than we've ever needed before, we leave the old buffer for the garbage collector to collect it. In this way, we avoid heap activity, but we stay correct. And the code looks simple and elegant. And I think this troika of fast, correct, and simple is the essence of D. And the third killer feature is metaprogramming. D's compile time features allow us to do things like generating code for packing and unpacking complex structures. It allows us to write code that's type safe and extremely efficient. This is where our big data solution, Swarm, gains so much benefit from being D only. There's just no overheads. And the fact that this metaprogramming is relatively painless is critical too, because all of our apps need to store their own data in Swarm. All of our programmers need to be doing some level of metaprogramming. The troika comes up again. The code is fast, correct, and simple. Three reasons are the core of why SOCIOMANTIC uses D. I think they're also part of the reason why any organisation would choose D. All three of them were of course, part of the original design goals of D. Binary compatibility with C was there right from the beginning. Array slices were in the first compiler release. And in my opinion, array slices are the big idea of D. That idea has shaped the language in so many ways. And D's metaprogramming, it's so obviously central to the language that it must have been part of the original design goal. If you read the original design documents, you'll read that right from the beginning, D was planned to be the perfect language for metaprogramming. Starting with its powerful template system, D would overtake C++ as the best language to do cool compile time tricks. That's what D set out to do. Let's look back at the history and see how closely the current language matches that original goal. What was the state of metaprogramming in D 1 decade ago? Well, Walter published the original spec for D back in August 2001. It was mostly written with reference to C++ based on his experience with writing C++ compilers. Firstly, he had a list of features to keep from C++. One was the first killer feature I mentioned, ability to link directly to C libraries. But the second part was more interesting. List of features to drop from C++. All the mistakes that C++ did. All the useless and problematic features. Multiple inheritance, preprocessor, digraphs and trigraphs, and templates. That's right. We don't need no stinking templates. All that metaprogramming rubbish those C++ people can do, they can keep it. D's not having a bar of it. Now, if you've joined D more recently, this may be a shock to you. D was explicitly designed to not be able to do this metaprogramming stuff. So how long did D stay hostile to metaprogramming? Let's move forward a few years. My next snapshot of the language comes from 2005. By then, a key feature of the language was, you guessed it, templates. Periodically, on the news groups, somebody will complain that Walter never changes his mind. Well, it's clearly not true if your argument is strong enough. The key contributor to D in those days was a C++ template guru called Matthew Wilson. Somehow he persuaded Walter that templates could look elegant if you improved their syntax and made the lookup rules sensible. So D began an unexpected journey. Sometime after that, D got two game-changing features, static if and static assert. Static assert is exactly like assert, except it's checked at compile time. Static if is exactly like if, except the condition is checked at compile time, and if it isn't true, the next bit of code doesn't get compiled at all. D also got some limited reflection capabilities in the form of is expressions. At the time, they were the messiest thing in the language. Personally, I can never remember the syntax for some of the more obscure forms. They work, but they're ugly. But that's where we were at. And yet, despite the underlying strong fundamentals of D, it was still defensive. The spec said, if a language can capture 90% of the power of C++ with 10% of its complexity, I argue that's a worthwhile trade-off. And this is the state that D was in when I first encountered it. It did not know what it had. That changed in the next 2 years. By 2007, the compiler had made a lot of guarantees about constant folding. These became more and more elaborate, eventually culminating in compile time function execution, CTFE. Now, in theory, almost any function could be run at compile time. String mix-ins arrived at the same time. I think they're best viewed as the inline assembler of generative programming. They allow you to do anything, which is both a strength and a weakness. And we got a few funny bits and pieces like string of, which is a big help for allowing libraries to produce nice error messages. And that's the state the language was in at the first D conference. A host of awesome new features, all added very quickly, and most of them didn't work. Well, that feature list was frozen and called D1. 18 months after that, SOCIOMANTIC was founded. And all our code is written against the language as it was defined in 2007. And so when I talk about our experiences, I'll be talking primarily about that subset of the language. But what's happened since then? D metaprogramming in 2013. Well, most of the D2 changes are related to constness, concurrency, and annotations rather than to metaprogramming. And for a long time, the most significant was arguably template constraints. Remember I said how much I hated is expressions? Well, template constraints clean up half the places where they're used. And traits address the other half. But they're even uglier. Well, it was something introduced as a temporary syntax. It's been temporary for 5 years now. That's a feature that is still in research mode. We really need to clean that up. And then all these cool things. Alias this, op dispatch, and these things would definitely be useful for us at SOCIOMANTIC. And then user-defined attributes, which are so new, the new frontier of D. I'm really excited to see where that goes. But most importantly, really, is that most things work now. You can write compile time code in today's D compilers and be confident that you won't get a nasty surprise. Why did I just go through this? Why did I just tell you this history? Well, I think it's important to understand a bit of the past to be able to understand the present state of the language. I think many D programmers have no idea that the language went in a radically different direction to what was originally intended. The language made minor steps and we got where we are by incremental improvement. And programmers have also slowly adapted. We've gradually learned new compile time techniques. But most importantly is that metaprogramming is an unexpected strength of D. We got here like miners following a vein of gold, not by an original master plan. And as a side effect of this, the language still has some junk left over from its history. If we'd planned to get here from the beginning, some things would be quite different. But I think we can be very proud of where we've ended up. Well, I've given you an introduction to SOCIOMANTIC and a little overview of D's history of metaprogramming. What happens when you bring the two together? From my experience in the history, I had a lot of ideas about what I'd find in the real world of SOCIOMANTIC. So I found 6 areas where experience challenged my expectations. 6 things that I've changed my mind about. And I'll share them with you. But all of them actually have one thing in common. There's a big idea behind them. The big difference between research and production. Return on investment. You probably didn't expect to hear an economics term in a talk on metaprogramming. But it's crucial. If we want D to be commercially relevant, the language has to make economic sense to use. Return on investment can be applied to quantities other than just money, but it's easiest to use money. You pay a cost and you get a benefit. If the benefit is greater than the cost, it's a good idea and someone will sell it. But actually that's not enough. Time is important. If the benefit doesn't come in your lifetime, it's pretty much useless. And when you're in research mode, you tend to focus on the benefit and forget about time. But in a production environment, it's the break-even time that matters. And the other factor we tend to forget in research mode is that if we want to persuade somebody that it will be attractive to pay the cost, including a cost like switching to D, the person who gets the benefit has to be the same person who paid the cost. And I'll show you what I mean with the first area where I changed my mind. Backwards compatibility. I went with a strong expectation that if a company has code in production, language or compiler changes should never break their existing code. They need that guarantee. Never break their code. Well, except sometimes you have to. Because sometimes bugs get fixed and codes break. It's inevitable. So, I fully expected that the programmers at SOCIOMANTIC would be screaming every time a compiler change broke their code. But the experience was actually different. Whenever a compiler breaks code, it's asking all the programmers to modify their code. They have to pay an upfront cost, however many hours it takes to make all the changes. But keeping misfeatures is worse because it's an ongoing cost. When we have something in the language that's just plain wrong, it's an ongoing cost. And it's easily possible for the ongoing cost of the misfeature to exceed the upfront cost of fixing it. In fact, that will normally be true for a language which is growing rapidly. But the problem is that normally the benefit goes to the whole language community, but it's the early adopters who pay the upfront conversion cost. The return on investment for the early investors might be very poor. And so things like gratuitous name changes have got very poor return on investment for the early adopters. Because name changes have benefits that mostly go to library writers, not to the users. You've already written your code. There's nothing in it for you. But there are some kind of breaking changes that are an easy sell. An example of one change we had with a very good return on investment was disallowing implicit fall-through in switch statements. Going through our code, I had to check the code change the code in about 30 places. In 3 of those places, there were bugs. 3 late-night debugging sessions averted. I could see the benefit as I was paying the cost. So, in those kind of cases, a breaking change can be met with enthusiasm. This is something I was not expecting at all. But in terms of return on investment, it's obvious why. If the person paying the cost sees the benefit very quickly, they want to pay the cost. The second of my 6 wrong areas was metaprogramming. I had very clear expectations about this. I did think that the situation would be better than in C++, but still, it's arcane. In C++, templates are cryptic and geeky. You have to have a strange kind of personality to really get into it. So, I expected that SOCIOMANTIC might have 1 or 2 library guys with a lot of C++ experience who might do this stuff on the rare cases where it's necessary. But certainly nobody normal would be using it. Well, sometimes it's good to be wrong. At SOCIOMANTIC, these techniques are used everywhere, not just in libraries, and even by new D programmers. Now, most people here have become involved with D because of a personal interest they have. But at SOCIOMANTIC, we have people who have learnt D against their will. We actually advertise jobs for C++ programmers. And then we tell them, after they've applied, we tell them, we don't use C++, you've got to use D. And in fact, some of our guys don't even have any experience with any language with templates. They're not all C++ guys. Some come from Python or Java. And yet, they're still using metaprogramming techniques. This is a big sign that the entry level is very low. Static if is a huge win. It's instantly understood. You can teach that in 2 minutes. The return on investment for learning that feature is just fantastic. And an odd thing that I didn't expect is that effect on morale. When people do some of these techniques, they feel clever. So they like using D because they get to feel smart. My third wrong area where I changed my mind was about error messages. I thought error messages have the lowest importance of any type of compiler bug. Because if your code is working, you don't get error messages. Nothing to complain about. If you do get an error message, well then just fix your code and then it's all fine. Experience. The interesting thing about error messages, good error messages make advanced features seem simpler. I think somebody referred to that yesterday. With C++, use templates, make a small typo, and you get pages of junk. The compiler spews its guts. And you think you're doing something really on the edge. Simple error message, you're doing something normal. Also, error messages have a teaching role. If the error message is well written, if the compiler can work out what you intended to do, it can teach you how to do it. It's a kind of public relations for the compiler in some way. And good error messages save time, and time is money. I think these are something that, to bash C++ again, I don't think they've thought about this at all. But when you get an error message and you don't, and it's not obvious what the problem is, you waste a lot of time. And when I'm in a company where I'm the compiler expert, I really notice how often somebody comes to me and asks, what does this mean? And something else I realised too was that error messages are actually the reason we use statically typed languages. They catch bugs. When we've got an error message, we've done something wrong. That's why we're doing it. Area 4, where I changed my mind. Compile time function execution, CTFE. And this is my baby. This is what I thought. Huge win, used everywhere. And so easy to use, you use it even when you're not thinking. And I thought that increasing the power of it, reducing the restriction, would increase the adoption. People would use it more. So I've gone to a lot of trouble to make everything work. You can use pointers, you can throw exceptions, you can create classes on the stack. Now, with the experience, well, I actually think in all those things I thought were true. However, SOCIOMANTIC hardly uses CTFE. It's just too slow. Fast compilation is addictive. Once your programmers are used to things compiling in seconds, if you do something that makes your compilation 5 seconds longer, people actually notice. The normal compilation time is so fast that it doesn't break your concentration. A few extra seconds actually makes a big difference to your thought processes. So, just as an aside, I have to mention why it isn't fast yet. It's because of the history. It was bolted on as an afterthought to the language. There's all kinds of unintended dependencies in the compiler. And a big issue was that to operate things in compile time, the front end has to be in a valid state. And so as I've worked on CTFE, it's been a matter of fixing up all the cases where the front end was leaving things in an invalid state. And I'm very close to making a big improvement on this. How close? A big step will happen when I'm going to make progress on the plane flight back. I've got 2 issues to do. A big increase in speed will be a while after that, but there's a fundamental problem very close to finish. 5th one, tutorials. Yep.
Before we get into this, can you comment a bit on how this dovetails with Maxime's note of yesterday? She said, it would be great if we had a JIT for CTFE on top of these fixes, which probably take care of the most painful aspects of it all. And then, JITting it all, it's going to be even faster.
Yeah. The problem with the speed is not that. How can I say this? The CTFE is kind of like a backend. You have a function and you need to compile it and then run. Conceptually, you compile it and then you run it and you return the result. The problem is with a normal backend, it only runs after all of the program has been semantically analysed, everything's finished, all error messages have been generated, and then you do code generation. In CTFE, you don't have that luxury. It's happening during the semantic pass. So any kind of errors in the front end are still there. Any kind of inconsistencies, an invalid syntax tree can happen. And so most of my work has been flushing that out. And until you've got a guarantee that you have a valid syntax tree, you can't even think about jitting or anything like this. You may be presented with garbage. And so this is a necessary step. So I have to get it to be completely consistent. There's all kinds of funny issues which I can explain to you later, but to anybody who's interested. But it's not as straightforward as you think, because inside a function it can refer to global local variables, which you think there's no such thing as a global local variable. Well, there is. They're a big problem. But yeah, this is the necessary first step. Yeah, this is a little one. The fifth point, tutorials. I thought tutorials were a waste of time. I mean, like, some people like them, but like, hardly adds any value. The experience is, it's really embarrassing. You hire a new guy. He got no experience with D. You've got to start training him on D. So he's got Python background. I've done all these Python tutorials. So where are the D tutorials? Where are the D tutorials?
dtutor.org.
Yeah. And final area was compiler bugs. I was expecting compiler bugs to be a disaster. There's thousands of open bugs in the Debugzilla. I was expecting to go into a war zone. But actually, there's a much smaller problem than I expected. At least in the subset of the language that we do, we hardly get these kind of template bugs, and it's a fairly rare occurrence. On the other hand, when we switched from 32 bits to 64-bit, that was a nightmare. But that was mostly a one-off cost that was borne by us. We were the first to seriously use the 64-bit compiler. So nobody else will have to deal with that. But otherwise, IDE bugs are much, much, much worse. I cannot stress that enough. The situation with IDEs is 20 times worse than with the compiler. We need more effort there. So there's my 6 areas. So the bottom line, D is moving out of research mode. All these kind of petty issues which we've been ignoring for a long time, and now's the time to start tackling these. I recommend this kind of return on investment model for thinking about really where are we adding value? How do we convince companies to use D? How do we add value to companies like us who are already using D? D needs to deliver value in the near term, not in the long distance term, not when we're all 100 years old. Our experience has shown that metaprogramming is a strength of D in the real world. Though it wasn't originally planned, this is a big strength of the language. And it does deliver return on investment for SOCIOMANTIC labs. We have actually made money with this, and quickly. But Some parts of the language, not. IDEs is a big one. We're losing money. We're losing a lot of money through the bad IDEs. So let's make it happen.
So you were mentioning IDE. D, indeed, due to compile time feature, let's take an example. In IDE, you want, for example, auto-completion?
No.
You want to...
No.
Or refactoring tool?
No. I want no crashes.
Yeah. Okay.
It's that level.
Okay. Let's suppose you have no crashes. You want then functionality.
Then I'm happy.
So yeah, as you say, let's just use VI in this case, or Emacs, or something.
Guess
that
what
doesn't
we
crash.
have to do.
Okay, so what do you want beyond that?
Well, yeah, syntax highlighting, but I do not want advanced features at the expense of stability.
Have you tried MonoD?
Oh, yes. No, that's it.
You mentioned, you mentioned quality of the error messages being a real high point of leverage. And how much of the problem with error messages in C++ do you think is the particular compilers like, Visual Studio C++ and GCC versus, say, Clang, where they've invested very heavily in error messages, and that's one of the features they brag about?
Yeah, I think Clang has realised the same thing. I think it's simply a matter that it was not thought of, it wasn't realised just how much leverage there is in this.
Yeah, I guess what I'm saying is, like, do you think D has something that makes it particularly well suited to providing better error messages that's a feature of the language as opposed to just the quality of the implementation of the compiler?
Yeah, that's a good question.
Well, you got the you got a user-defined error messages, fronting, and your work on showing part of the instantiation stack in template errors.
I think a big improvement would come from template constraint where it fails. That would be that would solve a lot of the current problems. That's the biggest source of unknown errors.
Yep.
I had one question is that you'd mentioned that you're using D1 Tango. At what point would D2 be good enough that it would be worth possibly moving to D2, or is that just not going to happen?
Well, it's the return on investment thing again.
Right.
The cost of a transition is very large. The biggest benefit actually is that we don't want to be isolated from the main community. We don't want to be the guys on the iceberg that drifted away from Antarctica.
Yeah, and the other thing I wanted to mention was this talk would be a perfect thing. I don't know if it could be put on the website as a why should our company use D? Because I've never seen a story like this.
You mentioned somewhere earlier in there that the ROI of things like name changes is pretty high and, well, or pretty prohibitive. But it occurs to me that should be something that is very amiable to tooling, is be able to say, hey, yeah, we changed the name of this thing, go in and apply this tool to your code, and it'll give you a sed script that changes all the places where you refer to that particular symbol and not some other symbol that happens to have the same name. How much of an impact would the existence of such a tool have on?
I think if there was a reliable tool like that, that would make a big difference. So that's a good example of, thinking. Yep.
I have a related question to that, especially since you are a big contributor of the compiler. To do such a tool in D, you need to almost have a complete compiler as a library, because due to all the compile time feature of D, you basically you basically need to have CTFE and stuff like that to provide this kind of tool, and so you need to have the compiler as a library. And is there some plan to do that? Like, what would be the work that have to be done with DMD to make this kind of thing happen, to make it reusable for something else than a compiler?
I don't really know. That's not my area.
To continue with Steve's question, are there any chances of using D2, at least in isolated areas, at SOCIOMANTIC? Your hires
it's something that we're thinking about, because it becomes increasingly difficult to maintain. There's an increasing maintenance burden on D1. It gets harder to factor bugs in. But as I say, there's a big transition cost.
But at least in isolated areas, some tools may be in D2. Is there any hope of D2?
Yes.
Do D1 and D2 binaries interoperate?
Could you repeat that, please?
Do binaries built with the two different versions interoperate with each other?
Yes.
At what level? Are you talking linking against each other?
Yeah, or even RMI. I'm just wondering if you wanted to phase in D2, what options would you have to work against the existing stack?
Look, we have plans for this. So that's under control, but frankly, it took us 3 to 6 months to move our code base from 32-bit to 64-bit. And nominally, there's very few changes, but we hit so many compiler issues with that. So we're expecting a D2 transition to be the same thing. For example, we use contracts very heavily in our code. And when we make changes, when we upgrade compiler versions, we very often hit bugs in these parts of the area, in these kind of areas. So I think we're exercising part of the compiler that not many other people are. So we're expecting unexpected costs.
All right, let's give Dan one more hand. Thanks, Dan. This is great. It's a very short break, 3 minutes. Thank you.